Friends, good morning to everyone. We were dealing with the synthetic strategies for peptides. We know that to synthesize the peptide of desired nature, we have to protect the amino group of one amino acid and activates the carboxy of the same amino acid and make it to react with the carboxy protected amino acid, and this will give you a peptide. Then we have to go for deprotection, and then we have to add the new amino acid and the process continues. And we know that there are two methods: solution phase synthesis, and also we have the solid phase peptide synthesis. Solid phase peptide synthesis has many advantages. And today's subject of discussion is the beginning of solid phase peptide synthesis, that is SPPS, and its development. Merrifield in the year 1963 used polystyrenic support. This is a resin made up of polystyrene which is chloromethylated. Typically, it is a divinyl benzene linked polystyrene. And this has been anchored with the carboxy group of the amino acid. And he used butyloxycarbonyl chloride for protection of the amino group. He used this because it can withstand strong acidic conditions. Later on, various polystyrenic supports were developed, and these polystyrenic supports were more labile, more easily cleaved, and many protecting groups were also developed which are more easily cleavable. In the year 1978, Fmoc based SPPS was introduced. The BOC protection was removed and replaced by Fmoc because of its more lability, more easily removability. Even now, the Merrifield resin is used rarely, and Fmoc protection has prevailed all these years. Let us look into the strategy of SPPS. In solid phase peptide synthesis, I take an amino acid in which the T represent the protection of the amino group, P represents the protection of the functional group present in the side chain, and this green bead represents the carboxy group. The carboxy group is anchored with the resin R. This anchored amino acid is deprotected, where the amino group which has been protected, it is cleaved to give rise to a free amino group. The free amino group containing amino acid which is anchored with the polymeric resin support, in which the functional groups of the side chains are protected, is made to react with the carboxy activated amino and side chain protected amino acid 2. They are coupled. The amino group combines with the carbonyl group of the carboxy to give rise to a peptide bond. This is the peptide bond which is formed. The peptide bond which is formed, again it has the protection of the amino group, and this is deprotected and coupled with another amino acid. And the process goes on until the desired peptide is obtained. Last step is the cleavage of this peptide which is formed from the resinous support and the deprotection of the side chains and also the amino group which gives rise to the desired peptide synthesis. Here R is the resin, T is the amino protecting group which may be BOC or Fmoc, P is the side chain protecting group as I already explained. Let us look into the BOC strategy. I take BOC protected amino acid and treat with the polymer. It is attached or anchored and the BOC is deprotected. The deprotected amino acid is coupled with carboxy activated amino acid and I get the dipeptide, and the process is repeated number of times and deprotected and cleaved to get the peptide or the polymer of the desired nature. The BOC approach needs highly toxic reagents like hydrofluoric acid and trifluoroacetic acid for cleavage from the resin. This is the limitation which we have here. That's why Fmoc protection is utilized. Fmoc protected amino acid is taken and treated with the resin. It is attached or anchored. Fmoc is deprotected to give the free amino group which is coupled with Fmoc protected and carboxy activated amino acid and coupled to give rise to a peptide which is deprotected and coupled with another amino acid the number of times until the desired peptide is obtained. Ultimately, it is cleaved from the polymer and deprotected to get the peptide and polymer of the desired nature. The BOC deprotection is carried out like this by using trifluoroacetic acid. The oxygen protonation occurs, giving rise to trifluoroacetate ion, and O group got protonated, making the oxygen here electron deficient. The pi electrons moves over here to satisfy the positive center, creating the positive center on the carbon. And to satisfy this positive center, the bond between the carbon and oxygen breaks and this forms double bond O and tertiary butyl group gets removed. Again, the nitrogen gets protonated and the lone pair of electrons in the oxygen abstract the proton and it becomes O minus. To satisfy the nitrogen positivity, the electrons over here moves, carbon nitrogen bond breaks and this becomes positive center. That's why the excess electron on the oxygen moves and loses carbon dioxide and gets the deprotected amine. This is how the amino group is deprotected, which is protected by BOC. The Fmoc is deprotected by using piperidine a secondary amine, a mild base. The acidic proton is removed from the piperidine, giving rise to the carbon ion, which is unstable. These electrons are donated and the bond is formed over here. To satisfy the position, the oxygen carbon breaks bond and these electrons are utilized the bond formation within carbon and oxygen, and the bond between the carbonyl and amino breaks and gives rise to DBF intermediate. The NH minus, which is electron rich, combines with the protonated piperidine and piperidine will become stable, and I will get the piperidine DBF adduct and the free amino group. DBF stands for dibenzofulvene. This is an easy deprotection using the mild base. That's why Fmoc protection is preferred over BOC protection. And we have seen the various amino acids side chains should be protected. How they are protected will be the subject of discussion for the coming presentation. Till the next presentation, have a nice day. Thank you.